Right, we're after the MGF of a Bernouilli, moment generating function for the Bernouilli distribution. And this is probably the most simple of the MGFs to find, and it's probably the first one that you're introduced to. Okay, so we're told to say that random variable x is Bernouilli, probability of success p, that's the parameter. So recall that x follows a Bernouilli trial distribution if we're interested in a single event, and that event, single experiment trial, and that trial has an outcome of success or failure. It's one of two outcomes. If we draw just do a little table of the outcome, say 1 is success, 0 is failure, and the probability associated probabilities, and what this is saying, that probability p of success, so it's 1 minus p of failure. So what I've written here is a probability mass function for x. Okay, so now on to the moment generating function, mt. We write down the definition. It's the expected value of this function e to the t times random variable x here, and let's do this on the side using the formula that if x is discrete, then expectation of a function, say g of x, g is a function of x, the formula says you sum over x of g of x times probability mass function, like so. Here the g function is exponential t to the x. Okay, so noting that the Bernouilli is discrete, we sum, not integrate, over the values of x. In other words, of possible values of x, well, the only possible values of x is 1 and 0. So let's say 0 and 1. And e to the tx times the probability mass function. Let's just say px. So let's put in the values. If we look at the first one, what this says is do e with to the t, and x is 1, alright, so just leave that, times the associated probability that x is 1, which is p. Okay, that's the first term dealt with. Oh, hang on. Let me reverse this. That's the wrong way around, because, it's right, but what we should say first is that this sum is going from x is 0 to 1, so first we have x is 0, so when x is 0, e to the 0 is 1. Probability associated with x is 0 is 1 minus p, so I should write this first. Alright, let's do it in brackets to show you that's the first term dealt with. Then I plus, and now set x to 1. That's success. So e to the t times x is 1 is e to the t, okay, times the associated probability of x being 1, and that's p. And are we done? Well, we've got to check, does this moment generating function exist for what values of t does it exist? Well, since we're not dividing by, we haven't got a fraction here, so we're not going to be in danger of dividing by 0. So it's pretty much for t on the real line. You can omit this bit if you like, it's this is the bit that you want. Okay, so that's it. That is the MGF of a Bernouilli. So, could you possibly ask me about doing this? Okay, to check that you've got a plausible answer, the MGF is a function of t, so you should have t in this expression somewhere. If you don't, it can't be right. Well, here you go, you've got t, right? Also, you should not have any x's in an MGF, because you've kind of the expectation of this function of x, the x will be summed out, so it's the values are given for the x's, so you shouldn't have any x's in there whatsoever. You should only have parameters, which I have. I've got p and I've got functions of t, and then that is plausible. Okay, in fact it's correct. what might we use this MGF for? Well, the next step is to use it to calculate moments, being the first moment, which corresponds to the mean, and the second non-centered moment, which I can use to compute the variance. So let's just write, because it's very easy to do. So let's say we want to find EX, which is called the first, and let's do it in brackets because some people don't use this in courses. They don't use expression. It's non-centered moment. Okay, and then EX squared is called the second non-centered moment. There you are. I've done one with British spelling and one with American spelling for centered. So there you go, one of each for the audiences. Okay, so first one, first non-centered moment, that's equal to the first derivative of this guy evaluated at t0. So first I need to find the derivative of MGF with respect to t, because that's the argument. Alright, differentiate. It's a sum of things. Differentiate each term by t. Well, that's a constant with respect to t, so that's 0. Plus, differentiate this guy with respect to t. Well, that's a constant times a function of t, so just put that there and differentiate this thing with respect to t. Well, you know the rule that if I want to do d over dx of something like a number, say a, oops, let's forget that, say a to the e to the ax, that is equal to e to the ax, and differentiate this guy with respect to x, a. So there you go. So what we have here is, well, a is 1 here, so it's simply going to be et. Therefore, my expected value of x, which is equal to this guy, is this thing at t is 0. Well, that's simply going to be p times 1, because it's e to the 0, which is 1. Okay, so done. Next, the second centered moment, that is going to be the second derivative. So let's do 2 slashes there for second derivative, valued at t is 0. First we need to get the second derivative. We've already got the first derivative here, so we just have to find the derivative of this with respect to t again, and you can see it's going to be e to the pt. Therefore, the second moment is, let's ex squared equals, second moment is this thing evaluated at t is 0. It is going to be p. Now we don't stop there because we have to calculate the variance, so we mustn't think that we've found the variance, like many students think they have finished. Variance of x then is equal to the second moment minus the first moment all squared. We've computed both these moments now. The second moment is here, minus the first moment is up here, but we want it squared, so there you go. We can leave it like this, but we can see it's a common factor of p, so just take the p out. 1 minus p. Alternatively, some people are observing that this is a probability of success, 1 minus p is probability of failure, so some people just say, oh, pq, where q equals 1 minus p. Okay. And that's it. That's a simple calculation showing you all you need to know about the MGF, really, how it's used, how to calculate it. And the MGF, just to finish off, the MGF for this Bernouilli is especially useful because it provides a short way, I think a nice short way to find the MGF of the binomial distribution. But that's for another video if you're interested. Alright, take care guys.